Good evening, everyone, and welcome. This is Professor Thayer with you here today to talk to you about working with cpptraj. Now, this is the second video in our series on cpptraj. Last week, we took a look at how to run cpptraj interactively, and as promised, this week we are going to take a look at how you can use cpptraj by making a script. So what we're going to do is we're going to repeat the activity we did last week, but we are going to take the log file and we're going to develop an inputs file for your cpptraj and go ahead and run that. So let me share my screen with you. Recall that I am working on a machine that uses Ubuntu Linux, and picking up from last time, we have run the Amber calculation using the cpptraj, and this is available for us here. And sorry, I'm just resizing my windows here. So let me just get this set up for you. So we are working on Linux, and we have Amber 20 installed on this Ubuntu machine. And just as a reminder, you can get Amber tools for free from the ambermd.org website. Download and install that on your machine, and you can also get the Amber package, the full Amber package, to run your MD simulations. You do have to pay for the license for that, and all the information is on ambermd.org. So if you are running Amber, then you surely already have the Amber tools, which includes the cpptraj package, the one which we are going to be using today. So I have just changed directories from my home directory to our Amber tutorials, and we have our 41A cpptraj directory here. You can, of course, name yours as you wish. And if I do an ls, we can see our work from last week. So I could go ahead and make dir to make a directory and make a new directory for today's. So we might call that cpptraj underscore script. Now I do use capital letters for my directories because it just helps me to remember which one is which, whether it's a directory or not, but that is just a convention that I use. And of course, when you do your ls, you will see a difference in the colors. As you can see here, the files are in this aqua color, whereas the directories are in this bolded lighter blue color. But I just like to do that as a matter of habit. Now what I'm going to do is I'm going to copy all of my contents. So if we do an ls, we see we now have the cpptraj script directory inside of the current working directory, which is going to then allow us to move our computation into there. So what I'm going to do is I'm going to copy everything. So I'm going to do star into cpptraj, and I can use the autocomplete and put a dot here for in that location or current working directory, which will be the cpptraj script directory. And of course, it cannot copy itself, which makes sense. So we can do an ls here and see that everything is fine. Now to just sort of clean this up, because now we have two things inside the 1A cpptraj tutorial, I am going to also make dir cpptraj interactive. I'll do int for interactive, and now I can move all the contents into cpptraj int, and that should not catch my directory. Let's see. And it can't move itself in there, so that's fine. And it did move. Let me go cpptraj int. Let's do an ls, and we see that it did move my cpptraj script version into there, which I wanted to be above. So now I'm going to do md cpptraj script to the directory above. So dot slash dot means directory above slash is in there, and then dot will be for current working directory. So let's do that. So no directories inside of here. Notice also that this portion right here is marking the current working directory. That's always helpful, so it's right in the prompt. So we see that we are in the int for interactive. That's the stuff we did last week. So I can do an ls minus L, and we see all of the things that we worked on last week on November 2nd, which was 1 week ago. Let's go up one directory and ls as we like. Now we have 2 directories in there. We have the interactive one from last week, and we have this one, the cpptraj script, ready for us to work in today. So let us go ahead and cd into the cpptraj script one. And we see we have a copy of our working materials right in here. Now, here we have the dist end-to-end.agr, which is the one that we hope to make already here. So that's kind of cheating. So I'm going to remove that one because we need to generate that again. Now let's do an ls. Okay, so here we have now our .nc, that's going to be our trajectory file. The parm7 is the corresponding parmtop file. We saw these last week. And here's my cpptraj.log from last time. So when we look at it like this, we have this idea that, maybe we've run something interactively and it's working, which is great, but maybe we want to put it into a script because we want to save the work, share it. Maybe you need to do this multiple times, and so you want something that's easily editable for running multiple runs, that kind of thing. It is a good idea that once you get your work actually bug-free, that you do want to keep track of your workflows, and putting them into a script is a really excellent way to do that. So what we can do is take a look at that cpptraj.log, and today we'll look at how we can actually build an input file for the for the cpptraj run based on your log file. So let us go ahead and just emacs that cpptraj.log. Recall that actually will run interactive, that cpptraj was run interactively, and it will automatically generate that cpptraj.log file. I'm going to open this using Emacs. You may also prefer VI or any other text editor, and I'm going to put the ampersand here so that I can continue working on this in this window here. So this just puts this into the background, which is great. And so, in fact, we see all of the commands that we gave. And this is already pretty close to being a cpptraj script. So let's just take a look at what we have got here. So here we loaded our parmtop. So okay, the date is put here automatically. So we see that this was around a week ago at 6:01 p.m. Great. And so here we are running a this is the parmtop file. We're loading that parmtop file in. Here we've listed the parm files. We got parm info. We talked about how that 0 will pick it out of the stack. We only had 1 in there, so that's pretty good. We also did the trajin line right here. Then we listed that trajin. We also got some information on the distance. We also got some info on the residues, the atom info on residue 13. The end-to-end distance. This was our calculation to get that dist end-to-end.agr. Then we did some listing. Then we had to actually run this command. And then we did xmgrace to view this. Looks like we maybe made some error in this, and we had to type this command twice to get the one we were interested in getting. And then we exited out of this. So that's a nice summary of all of the things that we did last week. Now that we know how to do this, and now that we have made all the selections, perhaps we don't need to do every single command that we did last time. And also sometimes in your log file, you'll get some things that are going to be, a mistake. Maybe you mistyped something or whatever. And so you can really clean this up then to make a finalized version of your script. So in fact, the script is going to look very much like this file. And in fact, what we could do is we could copy this file and actually just make it be our input script for for the cpptraj. So I think we'll actually do that because this is so very close. So I'm going to go ahead and do Control X, Control S, Control X, and Control C to close out of that. Now what I'm going to do is I'm going to copy cpptraj.log to cpptraj.in, which then will be a copy, which I will now edit to become the input file for our next cpptraj run. So here, let us go ahead and Emacs the cpptraj.in. And again, I'll do that with an ampersand. And so here we go. We don't really need this comment at the top because that's when the original one was run, and that doesn't really pertain anymore. So let's just put a note up here. cpptraj input script to calculate end-to-end distance. Great. So that's just a comment. We'll need to load in the parent file. Do we really need to list it anymore? We probably don't need to do that, and we probably don't need the parent info in the final version. These are things that would be more for working interactively. And once we are convinced that everything is fine, we can probably just go into production modes. We probably don't need that. Now here's our trajectory. And again, we were looking at some info on the trajectory, but once we are happy with that, we're all set. We would not really need to get help on the distance measure. And we probably also don't need the res info or atom info anymore, since now we already know which residues we want to use for making our selection for the calculations. We can take those out. Here is the distance command to calculate that distance, and that is the AGR file, which will be for XMGrace. Do we really need to list all the actions that are in the stack? We don't really have that much that is going to be being done, so I think we don't really need that because there's only one of them, and also we're not working interactively, so probably we just want to make the calculation. Don't forget, we do need to put that keyword run in there so that it actually executes the things that are in that stack. So that's great. Now there were two of these here, and as I recall, I think we had a typo in one of our commands here. So I'm going to guess it's the second one. So I'm going to go ahead and comment that out for the moment. And I'm going to guess that this is going to work like so. Also, we should just see how XMGrace is going to work being launched from the script. I think that's going to work fine on this machine. You may also want to not do that. And so again, I'm just mentioning that I'm working on the actual machine that's doing the calculation, which differs from the situation that you may be in. I'm SSHing into another machine. So if you are in that situation, like you open your terminal and you log into some remote machine, which we also do quite often in our lab, you would need to set up some sort of X-host forwarding so that you'll actually be able to see the graphics. You won't be able to see those across the port for the terminal. And so that can be a little bit of a pain. So some people choose to simply do their graphing on their local machine already. So they want to just do all their analysis. Like they run their MD simulation, they do their calculations of the end-to-end distance or whatever other calculations, and then bring the data onto their local machine and just do the graphing there. And so that can be a very good workflow. What you don't want is to have to do that and be moving large chunks of data. But oftentimes when you get to this point, this is just an output script. You're not moving your whole trajectory. So that actually is a pretty reasonable setup. And one that's often used. So let's just check and see how this is going to work on this machine and see if we are satisfied with our script. Notice that it is auto-saving for us down here. It's telling us that info in the status bar. So I'm going to go ahead and just do Control X, Control S to save it. And we see that it told us that wrote it in home, and Control X, Control C to exit out of that. Now we're going to issue the cpptraj command. It's going to be cpptraj. Now we're going to do the -I flag, and we're going to specify that input file. So it's cpptraj.in. And I can also do a -O and get a custom name for the output file. So we do have the cpptraj.log. So I do want to make sure that I name it something else. So let's call it cpptraj.dist, or maybe E2E dist, or end-to-end distance .log, and we should be good to go. So the -I points to the file that you are going to use as the input. So obviously that needs to exist on your disk, and the -O is going to be a new file that will be created when this actually executes. And ta-da, let's see how we did. All right, so it seems that it has opened us a window with the end-to-end distance, but as you can see, it did not, in fact, actually put any data here. So I think this was the problem we encountered last week as well. So I think I may have mixed up my file names. Let's take a look and see what we've got here. So I'm just going to do an ls -l to take a look at what files are here. So we notice that actually, I'm going to do ls -ltr, so it sorts it by time in reverse. So our newest files will be at the bottom. So you see that it has created our log file right down here. We can see that this is giving us the timestamp, and this is all today's date, which is great. These files, which were copied, have today's timestamp because they acquired the timestamp from when they got copied. And these other ones we see are getting their timestamps based on when we have last used them and when they got written. So this is good because we see that it has written the log file, and it's the last thing that it wrote. So we can actually check in the log file to see any errors. We did get that clue by looking at what the output was, and we see that it's called this end-to-end.agr. Now let me just try this before we get into here, xm grace, and then this end-to-end.agr. And here is our data. So we see that certainly the calculation has to run fine, and it's more just a question of debugging how that actually executes in our particular calculation. So this was the end-to-end distance of a small peptide, as you may recall. And so over the course of this simulation, we see that it is oscillating about a mean of about 6. We see that it does come closer together down here, and it looks like we have about 1,250 or so frames in here, and this is reporting on that distance. So we might also want to do some follow-up work up on this, like calculating a running average over some window or something to smooth this out a little bit or whatever, and also probably to clean up this axis. But certainly as a first pass, as a researcher, one might want to just look to see how the data is coming along. Did the calculation work? Is everything fine? And we see that certainly it looks like it ran correctly. This is a reasonable end-to-end distance for a peptide of this size, so the data is more or less as expected. And this gives you a basic idea. So not a publication quality graph at this stage, although you could use XM Grace to generate one, and you could spend some more time editing this up using all of these tools over here and whatnot. And you might even want to customize the graphing of your plot. But in terms of just a quick and dirty to figure out is everything fine, then it is. So probably I would then take this data and move it onto my local machine if I were logged in remotely. Here I'm on this one, so I might just work this up in XM Grace if I were interested in making a publication quality graphic for that. So it seems that everything is working. So I do see that this is the command that we want to be sure to have on our script. So let me just emax that cpptraj.in and check what we had put here. So we have XM Grace end-to-end.agr, which is wrong. We turned on the wrong one. So it looks like we got it right and then did it wrong. So let's do that. And this is the correct one. So you can see that you can go back and easily edit your script. This just more or less illustrates how one might do that. And so now we're happy with the changes that we have made. Don't forget to put exit at the bottom of your script. Control X, Control S, Control X, Control C to quit out. Now, just for the sake of completion, let us also just have a look at our logged file. So let me just Emacs the cpptraj E2E distance.log. That was the one that we specified on the -0. And here we see that what we saw last time printed on the command line is now captured for us in this script. So we did get the automatically generated script, but notice that that doesn't capture quite everything because some of it gets dumped onto the screen. So this is capturing the output that's actually coming from 2 different channels. So you're getting whatever is being displayed on the standard out, which is what you would see on your screen. And you're also capturing the output, which is going to be things that you had typed. So this is actually pretty useful and good. Let's see. So we see when this was run, we see the available memory, and we see that we are getting our commands here. So it's reading the input from cpptraj.in. Here's the parm file that we are using. We are getting all of this information that had been displayed on the screen last time. It's not having some certain information being specified, but that's fine because the defaults are what we need. Then we do the traj in of the actual trajectory, which is what's happening here. It tells us it's reading this in, and it tells us it's reading it in as the AmberNet CDF file format. That is because it was .nc, and that corresponds to the net CDF format. While in Unix, the extensions on files are generally not going to have the same level of activity that they would have in, say, a Windows operating system or a Mac operating system in terms of saying, like, this is what's going to open it. cpptraj is going to make some attempt when it's reading the input file to determine the format of the trajectory by the file extension. So it is useful to have that specified correctly. And last summer, we encountered some issues when it was .trj, which does not specify any particular format, and we had some issues with this. So if you're having problems, just as a tip, you might want to be sure to put the correct file extension. If you're running a recent version of Amber and have not made any specifications, so if you're, let's say, probably Amber 18 and above, it may even be all the way back to Amber 16, you are probably getting a net CDF that's a compressed file format as your default. And so if you name it .nc, you're going to have a much easier time working with it. Okay, so it said that the file time variable was defined but empty. Okay, don't know why that happened, but doesn't seem to be a problem because we have our times, our snapshots, so that's fine. The end-to-end distance, this was our command to do the distance measure. So notice that in the square brackets, this is where all the commands that we had in the input script have appeared in this, and basically it's then telling us the things that happened afterwards. And so then we are going to calculate this, and it's going to use the center of mass. So this, again, is not actually running the calculation because it's not going to run until you give the run command. So this is just telling you what it's loaded in terms of the calculation that it will be doing. So here we actually begin the run. And so here we have our parameter file, and we get additional information about that. And we also have our input trajectory, and it's running this. It's actually processing the read-in of the coordinates here. So we do see that it does a first pass at it, but this is where it's actually loading in all of that information to be ready for the calculation. So here we have some processing, and so the things in the stack for the processing are the end-to-end distance calculation, as we noted above. So here we go in the processing of this, and we see that it is telling us what it's calculating and some details about this calculation. We have one action, that is, we have just the end-to-end distance. If we had other commands there, they would appear in this stack, and you'd have more than one action. These percents are going to be reporting on how it's actually processing that. So you might remember that when we were watching this live by doing it interactively, we could see the 10, 20, 30 popping up on the screen as it processes through the trajectory. So it is a little bit not so useful when it is in the output file, except if you're having issues processing your trajectory somewhere, it does clue you in as to where that is. But generally you should see this going to 100, and then we move on to the next one. So it tells us about the average throughput as to how fast it ran it. Here we have the action output, the time, and the time analysis took was under a second. This was one data set, and it made the end-to-end calculation. And here is some info about the size of that and the memory usage that was required for this. So these stats actually can be helpful if you are going to eventually make some cpptraj scripts that you're going to need to submit on the cluster, because what you're going to need to do is allocate some memory to run those calculations. And if you haven't done them before, you're not going to know how much you actually need to use. But when you do it like this, you'll get some information. And so if you do multiple calculations on similar systems, maybe you have like some mutants or some different sequences or whatnot, you'll get a pretty good idea of what kind of memory and so on you'll need to allocate. So this can be really useful if you are planning on doing some scaling up, because it will give you some basic parameters that you will need to use. Here we have the data files. So we created one data file that was the dist end-to-end.agr, which is an XMGrace file. Again, it does use the extension in some regard in ways that's a little bit uncharacteristic for Unix, but it does signify that the AGR is going to be for running with XMGrace. So it writes it out in the format that includes all of the wrapper text and commands and whatever are needed by XMGrace to actually make that plot. So it puts those headings and things on for you automatically by pulling info from your run. And so if you had just output it as a plain text file, you just get basically an XY column, but by doing it in this format, it does make it a little bit nicer. So you can do that .agr, and that does have that significance to cpptraj. And then finally, we get some stats on how long this took to run overall. It tells us how long it took to initialize the calculation, the trajectory processing, action post, the analysis, the data file writing we see is one of the longest things. So it took us 0.002 seconds, which was 62.52% of the calculation time. And the writing out of the data file also is one of the more time-consuming ones. That was 36% of the calculation happened here, and other for any other processes. So of course, this is a really quick, just a toy model problem, but when you are working with larger data sets, these stats can be quite helpful for your planning on how long a project is going to take. There are some cpptraj runs, like we do correlation matrices. Those are going to take on the order of days sometimes to run, hours to days. And we also run some calculations that involve doing cluster analysis, and those tend to take several days, maybe even up to a week for some of the bigger ones. So having these stats, again, is just super helpful for your planning of your project and so on, and to see how your system is working. So this system is pretty quick, and we see that this was really fast. And so these stats may not be particularly meaningful, but you can use these to, perhaps see if there are ways you can speed up your calculation by sending it to different queues and so on, to see the difference in how long it's going to take. And so the total execution time was 19.45 seconds, although how that works out from these times here, I'm not totally sure how one picks up those other 19 seconds, but usually these are all going to be things that are pretty short. So anyways, it was a really quick analysis is the bottom line. And finally, we get the information about these way that we can cite the cpptraj. So if you are writing a paper on this for your project or writing a publication, you should cite Tom Cheatham and Daniel Rowe's work by using this citation. All right, so that's our log file. Very helpful. If there had been any errors, that might be an excellent place we could find that to do the troubleshooting. So that's terrific. Let us go ahead and just do an ls minus L here. All right, so we see we have all this information. Notice also we get this tilde file. This is cpptraj.in, and then we also have cpptraj.in tilde. This is a Unix thing where it makes a backup copy of a file when you edit it. So maybe you did something and say, oh, I just ruined my file. I just deleted the critical data. You can go back to a tilde file, which will always be the most previous most previous file that you had. So I usually leave them around for a bit, and then when I'm finishing up my project and I'm sure that I'm happy with it, I usually remove those to just clean up my directory. All right, so then let us do an ls minus ltr. Here we go. That's great. So the next thing I want to do is, now that we have made those edits to the input file, I would like to go ahead and rerun the calculation. So what I'm going to do is I can use my up arrow to go through my history. Oh, there's our calculation, and this will dump our information into the log file. So let's go ahead and run this another time. That's really fast. Doesn't even look like that was 19 seconds. Interestingly enough, the XMGrace does not plot correctly out of the script. So for some reason, it seems to, I'm going to just do this. And now I'm going to do XMGrace and then dist end-to-end.agr, and it works fine. So it seems that for whatever reason, it's not working properly out of the script, but it is working outside of here. So what I'm going to do is I'm going to go in and I'm going to edit my cpptraj.in script one final time. And so what I'm going to do is I'm actually going to turn off the calculation of the actually doing the plotting. So what I'm going to do is I'm going to just put a note here: to view your plot, use XMGrace dist end to end.agr. So we'll know how to view that data, to view plot in XMGrace. And so this is actually maybe even a better setup, because you may not want your plot popping up anyways, and then it will do that for you, and you can do your data when and if you wish to do so. All right, so then we can do this. We could now run this one final time. There we go. And then we do an LTR, and notice that it told us that it is putting our output to the screen into cpptraj end-to-end dist.log, which is exactly what we had wanted to do. We still have our old log file here, so since we're not using that, we can remove this log file, because this, of course, is the copy of the directory where that calculation was actually done. So the original really belongs in the original one. LTR, and here we have this. So now we can, looks like everything's working. We can remove all the backup files, star.tilde or star tilde. That will remove, so star matches anything, and tilde is for that symbol that is appended to our calculations. And we see that we have everything here. And so now, just to review, we have our farm file, our trajectory, the input file for cpptraj, the end-to-end distance.agr data, and the log file from running the calculation. Before we sign off, one thing we probably should do is we should probably just do a head of the actual AGR file, or let's just open it. Let's do Emacs dist end-to-end.agr, and we see that we have these headers on here, which is used by XMGrace to set this up, and you can pretty much see how this is working here. Notice it is setting up the x-axis label, the frame, and there's no y-axis label. So one could easily go into here and edit this in order to create a custom graph. So here we have our legend character size, the legend name, and so on. And then we have our XY data being shown here. And so this is everything that we saw. And we can see that we have all these data points and that they are mostly right around 6 or so, as we had seen in the graph itself. So if you did want to clean this up and make a publication quality version of this, you could perhaps go in and edit this. So shall we go ahead and do that? Let us copy the xmgrace file, dist end-to-end.agr to dist end-to-end, and I'm gonna do underscore pretty dot agr. Now let us go ahead and Emacs that, and pretty.agr. I'm going to put this with an ampersand because this is going to allow us then to work with this interactively. So maybe I don't like the x-axis label frame. Maybe I want it to say instead time in nanoseconds. And I want a y-axis label, which would be distance and angstroms. And okay, so here it says the legend is running from 0.2 to 0.995. I think those are the labels on the x-axis. This is the character size, and the legend says end to end. All right, so let's go ahead. Don't forget to save your file. And now let us go ahead and run the xmgrace. And now let's do dist end-to-end underscore pretty dot agr to run our graph. So let's see if we can view any of our changes being implemented. So, oh, I see the y-axis now has a label, and my x-axis has been updated. Although those probably are not nanoseconds, that's picoseconds. So this is wrong. This is going to be picoseconds. And here we have the angstrom. We have our legend up here. What I'd really like to do is to change the y-axis. I do not know what the key is for the y-axis, but I could maybe perhaps guess. This here is for the data. And here, this is for our legend. This is our character size. I'm going to hazard a guess at how I might format the y-axis. So I haven't looked this up in the manual. I'm just going to go with y-axis max 1500, and let's see if that works. We'll do a little experimentation. What do you think? So you'll see what this allows me to do then is to close that up. Now I can come back over here. By the way, you see I have the transparency set on this, which is super convenient because I can just see the ghosting behind of my previous script. So now I can choose my up arrow to run that graph again, and let us see. Luckily, we didn't get any errors. Okay, it did not truncate my labels as I had wished it might, but we do have the other edits. Did I save this? Yes. Okay. Next. And let's see if we can do this again. And do this. Oh. No. All right, so we'll need to look at the XM Grace manual. Let's see. XM Grace. How to set X Grace tutorials. Let's see. Plot functions, graph operations. Let's see. Introduction, making data set appearance. Yeah, I think we want this. Yes. My formula. Okay. All right. Well, anyways, what one might want to do is just read through this manual. I'm sure that there's information on how to, in fact, actually do the how to, in fact, actually set the maximum for the y-axis. I wasn't really planning to do all this editing of the graph here today. But anyways, this gives you some sense of what the kinds of things that you can do here. And XM Grace is pretty fun. Oh, look at that, what I just zoomed in. So I think you might actually be able to do this automatically. Oh yeah, see, you can change your zoom level. This is zooming out, zooming in. Can I pan up and down? Oh, I can pan up and down. So you could, in fact, actually just edit your graph by using these. I wish that it would. I wish that it could zoom in on the y-axis. Auto T. What's this? Auto O. UI. Let me see if I go like this. What does it do? Nope. Zoom to this area right here. There you have it. Okay, I've just edited the axes and now I can move this over just a tad bit. Up, down, and we can center this in here. So you could do this in order to edit your graph. Yeah, this is actually pretty convenient, so you don't have to actually know beforehand. Yeah, it's been a while since I've used XM Grace, but it is a pretty powerful plotting system. So you may want to play around with this yourself a little bit more because this is really good. I see you could make a pretty nice graph pretty easily. I'm just fooling around with all these things to see what I can get here. But look at that. Yeah. It'd be all done in a couple of minutes by just zooming appropriately. Yeah, so the key thing here is working with your magnifying glass and zooming in and out. So yeah, there you have it. That's a pretty decent graph right there with the cutoffs of interest, and it's zoomed in so you can see your data, and this is clearly just about at 6, which is what we had seen before. So I'm sure you can actually script this up. Spend some more time reading the XM Grace tutorial so you can see about that. I just looked that up online. And here you have a beautiful graph which you can draw right on your computer. All right, well then, I think that will conclude. Our exercise for today. Let me see if I can just save this. Can I do save as? And say, okay. My graph. There we go. All right. And let's take a look at what we've got here. All right, I'm going to star tilde to clean up the directory. And we see that we, in fact, have my graph in the output. So there you have it. All right, so in summary, last week we looked at running cpptraj interactively so that you could work on understanding your data sets. We saw how we could get information about the items that are in the stacks on your cpptraj. So you could read in your trajectories, you could read in your parm.top files, you can also set up some calculations to be run, but don't forget that it doesn't actually run them until you use the run command. So we saw how we can do that, and we did all of that interactively to get a feel for how the calculation was going and to make adjustments, learn about our system and so on. But once you get beyond that, you probably want to get in the mode of scaling up to run lots of calculations and or to keep a record of the calculation that you're doing. And that's what we had to look at this week. So this time we took the output from the log file from running the calculation interactively, and we just went ahead and put those commands into an input file. We were able to modify that from our cpptraj log file. So we just called that our input file, made some edits to that, put a comment at the top, and we were good to go on that calculation. And now we have run that, and we see that we can graph our data in XMGrace. We did take a little bit of time to play around with XMGrace. So I hope you enjoyed seeing how that could be done and seeing how the data flow actually works in real practice. This is what it's like when you're sitting down at your computer working through things. So I hope you've enjoyed doing that with us today. Thanks so much for joining us. I hope you like and subscribe, and we hope to see you next time for our final installment of the cpptraj from the fall 2022 season. Thanks so much, and hope to see you next time.